Okay, so in this set of notes, we are going to look at some more chemical bonding. We're going to talk about polar molecules a little bit, and then spend a lot of time talking about hybrid orbitals, which is pretty cool, and then talk about bonds, double bonding and single bonds, and what those look like. So molecular polarity. We already talked about polarity in different bonds, just looking at two different atoms bound together. But now what happens if you look at a whole molecule? Well, we looked at the diatomic molecule. The dipole moment is just a measure of the magnitude of separation of charge between the two atoms, like we've already seen. For a molecule that has more than two atoms, though, we look at the whole molecule to figure out the dipole moment. So that basically means you need to know the molecular geometry to know what the molecule looks like. So for example, if we're looking at H2O here, you guys know that the oxygen is more electronegative, so the polarity, the dipole movement goes positive over here towards negative over here, and because this guy is bent, overall the molecular dipole is going this way towards the oxygen. Kind of the same thing going on over here. Because that fluorine is so electronegative, everything's going to be kind of going that way. However, if bond dipoles are equal magnitude and opposite in direction, they're going to cancel each other out. So like this guy right here, right, you're going to have equal pull up by both of those oxygens, and they're both pulling in opposite directions, so the overall net dipole is 0. Okay, so let's try a couple examples. BrCl, pretty simple. Just do your diagrams, Br to Cl. Who's more electronegative? Chlorine's more electronegative than bromine, so you're going to have a dipole moment like that. So this is definitely going to be a polar molecule. How about SO2? Well, we got to draw our molecule. S is going to be in the middle. We're going to have some oxygens over here, and we fill in our octets. In this case, we're going to put a double bond on one of these oxygens over here. You got some free electrons. Now we also have some resonance on this structure. You can move the double bond to the other side, or you can move these electrons down and do two double bonds, but again they're resonant, so they're all equally the same. But no matter what, these guys all have the same shape, right? It mostly looks linear now, but we have the electrons exerting some force here, so this is actually going to be a bent molecule. And then obviously oxygen being more electronegative means that our dipole moment is going to go from the sulfur towards the oxygen for both of them. But since we're looking at a bent molecule like this, our dipole moments are going to be going like that. And so overall, we're going to have a net dipole moment for the whole molecule going towards those oxygens. So yes, it's going to be a polar molecule. And finally, let's going to look at sulfur hexafluoride. Remember, sulfur, because it's a little bit bigger, doesn't always follow that octet. Well, fluorine is going to be more electronegative, so we're going to have an overall dipole moment going towards fluorine. And basically, they're all the same, so each one is going to cancel each other out. Like this fluorine dipole is going to cancel out this dipole, and this one, this one, this one, this one. So overall, this guy is not going to be polar. It's going to be a nonpolar bond. This next slide really just codifies what we've already been talking about a lot with covalent bonds and electron sharing and things like that. Basically, the valence bond theory says that electrons are shared if their orbitals overlap. So in that area of overlap is where the electrons are going to be concentrated. Right in there, right in there, right in there. Let's stop. So within that bond overlap, there is an optimum distance between the nuclei in any of these covalent bonds. So if atoms are really, really far apart, they don't really feel each other, right? No, I don't feel you, man. They're not really exerting any energy on each other. But as they get closer together and those orbitals start to overlap, the potential energy of the whole system is starting to decrease, right? So there's less ability to move because they're starting to bind to each other. That bond strength increases. So you keep in closer and closer and closer and closer together, the bond strength is getting stronger and stronger and stronger. However, if you get too close together, the energy then starts to increase because now you're running into electrostatic repulsion going on from those two actual nuclei. So the bond length really corresponds to the lowest amount of potential energy between the two nuclei. So the attraction between the electrons in the nuclei balances the repulsion between the nuclei and between the electrons. So that's the maximum attractive force. That's the distance, and that's also the bond strength. Okay, so this next topic can be kind of tricky. It's kind of interesting, but it's all about hybrid orbitals and how some of these bonds work. And we've kind of noticed this in class a little bit. So if you look at the electron diagram for carbon, you look at our energy levels, how many bonds would you expect it to make? Well, if we look at this down here, we're only seeing really just two unpaired electrons. So you'd expect it to make two, right? But what do we know about carbon? Well, we always talk about carbon having 4 valence electrons, and carbon's very good at binding with 4 other things. So clearly, these things aren't jiving, right? They're not going together. So we need these hybrid orbitals to explain how you get these certain geometries. So like how carbon combined with 4 other things. So hybridization occurs when 2 orbitals on one atom mix to form 2 new orbitals. They're called hybrid orbitals. And the shape of the hybrid orbital is different from the shape of the original orbital. So we're going to take a look at those. So the first hybridization that we're going to look at is sp hybrid orbitals. This is formed when you hybridize an s orbital and a p orbital. So for an example, we're going to look at beryllium difluoride. So this is a linear molecule with 2 equal beryllium fluoride bonds. Fluorine has 1 paired electron in the 2p orbital, which can overlap with any beryllium orbital that contains an unpaired electron. So, okay, sounds good. That's what we've been talking about all along. But if you look at the orbital diagram for beryllium, this is what you see. Do you have any unpaired electrons? No. So how do we solve this? Well, a 2s electron could jump from 2s up to 2p. We've been talking about that. So beryllium would now have 2 unpaired electrons, but these orbitals are not equal. Right? The s and the p orbitals are not equal, so that doesn't explain the linear geometry. You wouldn't get a linear molecule, which we see experimentally. You wouldn't get that if this were the arrangement. So something different needs to be going on, right? So what happens are the 2s and the 2p orbitals mix to create 2 new orbitals that are equal to each other and point in opposite directions. So you got your s orbital and you've got your p orbital, if you remember those shapes. Those guys mix together and basically look like this. Okay, and now we have a kind of a new orbital diagram for the beryllium. You've got your 1s, which stays the same. Now we have sp, right? And then if you look at our p orbital or 2p orbital, there's only 2 spots instead of the 3. So this guy came over here and joined up, and they formed an sp. So this is our old 2s and our old 2p1. Those are now together as an sp orbital. And so if you look at this shape down here, now we've got a nice linear molecule. It's bound up with those fluorines. Everyone's happy, and this explains things nicely. So that covers linear molecules, but what about some of those other shapes? Well, as you need to, you can pull down more p orbitals to hybridize. So however many orbitals you mix equals the total number of hybrid orbitals you produce. So a 2s and a 2p hybridize to provide or make 2 sp orbitals. 3 sp2 orbitals are formed from an s orbital and a p orbital. Okay, so you've got your s and you've got your 2p orbitals. Those guys all combine together to get this guy here, which is going to give you our characteristic trigonal planar shape. So whenever you see something that has a trigonal planar shape, you know that you probably have this sp2 going on there. And then if we look at the 4 sp3 orbitals to get us a tetrahedral shape, we can see that we're taking that s orbital and taking 3 p orbitals. So a really good example of this is carbon, which we started off with. Right? So our original orbital diagram is looking like this, and we said, oh wait, we only have 2 electrons that are good to pair. Well, if we form some hybrid orbitals, we're going to take 2 of our 2s electrons, and then we're going to take our 2 of our 2p electrons, and they're going to form up these 4 hybrid orbitals, this sp3, and these guys are now going to disappear. And our electron diagram is going to look like this. So now we have our 4 electrons that are there to bind with other things and give us our tetrahedral shape. You can also use hybridization to describe the non-bonding electrons in the molecule too. So this guy still has like that tetrahedral electron domain geometry. So you have to take that into account. So when you're doing these things, you take your molecule, draw your Lewis dot structure, right? How many electron domains does this guy have? 1, 2, 3, 4. So that would be a tetrahedral. And what shape makes a tetrahedral, or what hybridization makes a tetrahedral? That'd be the sp3 hybridization. So it's going to look something like that. All right, so let's try an example. Let's look at NH2 minus. So if we draw our Lewis dot structure, we got this guy here. Our electrons, the whole thing is minus. All right, well, how many? All right, so we've drawn our electron domains, or our Lewis dot diagram. How many electron domains do we have? 1, 2, 3, 4. So that would be a tetrahedral, or 4 electron domains. So in order to get that, we need to have an sp3 hybridization. Okay, next we're going to talk about what happens when you have multiple bonds or even single bonds going on. So a single bond is just called a sigma bond. We have the overlapping orbitals are in line with the nuclei of the 2 bonded atoms. So single bonds are always going to be this sigma bond here. Okay, your p orbitals in this instance are lined up. Here's where electrons are overlapping. A pi bond, just like in math, is a double bond, but this results from the overlap of 2 p orbitals that lie above and below the atom's nuclei. So remember how sometimes these guys have 3 different axes, right? They could be this way, or kind of straight up and down. These are the straight up and down ones, and they bond the sides of the lobes, like these parts right here are what are binding. And so that's how you get this double bond. Right? A double bond consists of a sigma bond and a pi bond. That's why those bonds are a little bit shorter, because these guys, they have to be closer for these guys to bond. So a pi bond is a shorter bond than the sigma bond, which is why double bonds are shorter bonds than single bonds. Okay, as an example of this, let's look at this molecule here, which is this ethylene. And so here's our Lewis dot structure right here. We've got the carbon double bonded and the 2 H's. So first off, let's just take a look at this and count up some of the bonds. So how many sigma bonds do we have? Well, these are easy. 1, 2, 3, 4, and one of these guys is going to be a sigma bond. So we have 5 sigma bonds. How many pi bonds do we have? Well, just the other one in that double bond. So we have 1 pi bond. How many electron domains do we have for each of these carbons? 1, 2, 3. We have no lone pairs. We have just 3 electron domains. So what kind of hybridization do we have? That means we have sp2 hybridization, which is going to look something like this. Okay, well, that should say sp2 right there. You've got your 3 electrons to bind, and you have 1 electron that's still left up there in the original 2p orbital. Okay, so if you look at this over here as we're going down, we've got our sp2 hybrid orbitals, so kind of that trigonal planar shape. So these guys are going to overlap there. There's a sigma bond. Okay, then we also have these guys that are sticking up. Those guys are going to bind with each other as well. So there's our double bond going on. Then we've got our extra sigma bonds over there binding with our carbon-hydrogen bonds. So that explains double bonds and why double bonds are shorter than single bonds. Okay, so the last thing we're going to talk about is resonance structures and how that affects something called delocalization. So here we have our same carbon with sp2 hybridization, which means we've got some 2p orbitals sticking up. So this is like a benzene ring. And then these guys, when they bond, so we got our double bonds, those could be considered localized because they are bound to specific orbitals, specific carbons, right? And remember, since this guy has resonance, this guy could double bond to this guy, or that same carbon could double bond to this guy over here. So when we look at the whole thing in the resonance, right, their whole molecule basically looks like this. Now we say these bonds are delocalized because they have options. So basically, if a structure has two or more resonance structures, we could say that those bonds are delocalized.